And here is the title of the talk. It's Low Frequency Phase Diagram of Graphene Under External Radiation. And that's a work done with my student Bhaskar Mukherjee and postdoc from HRI, Priyanka Mohan, who was probably working with Sumathi, and Professor Diptiman Sen from IACS, who has been a long-time collaborator. So here is a brief outline of the talk. First, I'm going to give a very brief introduction of periodic band and talk about phase bands rather than Fluke Hamiltonian, which and its relation to change in topology. Then talk about role of symmetry of the graphene Hamiltonian in the presence of external radiation, which is going to play an important role in sort of detecting this topology change. And introduce this adiabatic impulse approximation, which has been used to obtain analytical insights to our data. Talk a bit about the phase diagram and chart number calculations, although I don't think I'll have time to go into the last topic. So let me introduce this. Give a very brief introduction to a periodically driven system. So what I'm going to be concerned about is a closed quantum system where one or more of Hamiltonian parameters are driven by some periodic function of time, so that you have a periodicity out here. And these Hamiltonians could be either integrable or non-integrable, and these are the features, but I'm going to basically talk about an integrable Hamiltonian in this talk. Okay. So typical theoretical treatment of this kind of systems rely on high frequency expansions, and there are various kinds. I'm just going to talk about the most basic one, which is called the Magnus Fluke expansion. So what you do is that since it's a time-dependent system, you concentrate on the evolution operator, which is given by time-ordered exponential of the Hamiltonian, and then the state after n periods of the drive is simply u of t to the power m psi naught, because ut is a periodic function, right? So the standard Fluke theory allows us to write ut as a product of a periodic part p and a term which has this Fluke Hamiltonian, and this is analogous to block theory. Just as a block wave function you write as a periodic piece in space as well as e to the power I k x factor. This is the analogous of time. Okay, analogous in the time domain. So essentially at t or so if I now evaluate this expression at t equal to 0, you find that p of 0 must be 1 or up to some phase factor. Because p of t is a periodic function, this means that at every capital T or any integer multiple, this has to be 1, and therefore the unitary evolution operator can be simply represented in terms of the Fluke Hamiltonian if you are evaluating it after integer number of drive periods. And then you could take this and that and do a systematic term by term expansion, provided your capital T is small or your frequency is large. And that's called the large frequency expansion. It depends on the smallness of t or 1 over omega. And to 0th order, you find that the Fluke Hamiltonian is just then the time average of the Hamiltonian, and there are other terms. So this is the Fluke Magnus expansion, which is a high frequency expansion, and it relies on 1 over omega, smallness of 1 over omega. Okay. Now, people have used this to study several systems, and the system that I am going to be concerned about is this graphene in the presence of external radiation, which has been studied by several groups. And here I have taken some data from Takashi Oka and Hidei Aoki's paper. So essentially you put this graphene under external radiation and calculate an effective Hamiltonian, which is done somewhat similar to, in a manner somewhat similar to Fluke, this Magnus Fluke expansion. And then you look at this Fluke band. So since you have this Hamiltonian, you can find the eigenvectors corresponding, the wave functions corresponding to this, the eigenfunctions, and consider the Chern number of this. And you find that as a function of frequency and amplitude of radiation, these Chern numbers undergo a change, and therefore you have a dynamics induced topological transition. Okay. And here is the phase diagram. So at large frequency where there is analytical input, you see that there is a very clear structure where it changes. These are the Chern numbers and it clearly changes. But in the low frequency regime, it's a zoo. Okay, and there is very little understanding, at least theoretically, at least from what I could find in the literature, what happens in this low frequency regime. And that's the subject of this talk. And so the analytical approach in this regime depends on the smallness of 1 over omega. However, that breaks down here, and in this low frequency regime there is no existing analytic method as far as I could scan the literature. And the question is there a possibility of an analytic approach to obtaining Fluke Hamiltonian for the low drive frequency regime? And I'm not going to get into the details of this, but it turns out that when you study this kind of topological transition, it was shown that studying Fluke Hamiltonian is not always enough, because transition can take place between 0 and capital T. So it's necessary to follow what we call as the phase bands, which are essentially eigenvalues of the unitary evolution operator themselves. Now this unitary evolution operator is a unitary operator, and therefore the phase bands have the following form. And this phi n as a function of k and t can be related to the Fluke spectrum if you evaluate them at the end of a period. Okay, so that's the relation out here. So this contains the Fluke Hamiltonian if you are looking only at capital T or integer multiples, but this is more general because you can, if you calculate them, you can track the system between 0 and capital T. Okay, also within a given period. And topology change occurs when these phase bands cross, and again I'm not going to get into the details of this because of time, but the point is that whenever you have a dynamics, there could be two types. One in which these phase bands coming from different zones never cross each other, and they are analogous to dynamics where your Chern numbers do not change. However, there could be dynamics where they do cross, and within this crossing there is a change in the Chern number. Okay, these crossings act as source and sinks of Chern number when you compute them, and this phase band dynamics during periodic drive indicates possible crossing between the different Chern numbers of this system, and that's what we are going to pick up. Okay. So, okay, let me not get into this. So let me just directly go to graphene and talk about the model. So what we are going to be concerned with is graphene under external radiation. So excuse me. So this is a circularly polarized light with amplitude A naught and the following frequency dependence omega. And so if you just do some power substitution, you find that that's the Hamiltonian of graphene that's going to come in. So there are some phase factors, and here I'm going to go for the tight binding model of graphene because I'll be interested in different parts of the Brillouin zone, which is not necessarily described by a Dirac theory. So the different parts are given by gamma, the k points where you have these Dirac cones, but also the m and the x points, which are different points in the graphene Brillouin zone. Okay. So you take this Hamiltonian and you do some harmless unitary transformation, and you can show that this Hamiltonian for any k can be written as a 2 by 2 matrix with some diagonal component c of k and off diagonal component b of k, which are essentially real and imaginary parts of this Z. Okay. And therefore, the instantaneous energy levels which are given by this mod Zk are essentially square root of c square plus b square square root of that. Okay, so that's the standard. So the first step towards our analysis would be analyzing the symmetry of Hk and Ek at several high symmetry points. Okay, and I'm going to basically talk about gamma, k, m, and x. Okay. Now, here is a picture of the instantaneous energy levels in the period in the presence of the drive as a function of time from within a single period. Okay, so panel A is gamma point, panel B is k, panel C is m, and panel D is x point. Okay. So that's and the amplitudes etc. are given here. But the first thing we notice is that the symmetry of these instantaneous Hamiltonian energy levels are different from capital T. Okay, that's probably obvious here. You see the repetitions and you see that it must have a lower periodicity. So we analyze the symmetry. So in the gamma point, it turns out, and this can be shown analytically, which is there in our paper, the Hamiltonian turns out to be T by 3 periodic. It's not T periodic. And the eigenvalues, the instantaneous eigenenergies are T by 6 periodicity, has T by 6 periodicity. Now, so so the point is that at the gamma point, the symmetry of the Hamiltonian and equivalently the unitary evolution operator is lower than, has a lower, so it has a lower periodicity compared to the drive time. Okay. So drive time period, and that would be important. So here is the symmetry for the Dirac, the M and the X points, but the bottom line is that in all other points the Hamiltonian is T periodic, whereas the instantaneous energy values could have different periodicity, okay, which is here. So now let me introduce this adiabatic impulse approximation, which we will use to calculate these phase bands or the eigenvalues of the unitary evolution operator. So the approximation is very simple. What one does is that, so when we looked at this, let me just show you this. So when we looked at, let's just take this, okay. So when you look at this, you see that there are different points in time where these bands, instantaneous energy bands, goes through an avoided level crossing, and at other points the gap between the two levels is large. Okay. So in this adiabatic impulse approximation, we use this fact and we say whenever the gap is large, the dynamics is adiabatic, and excitation production, whenever it happens only in this avoided level crossing region. Okay. Now this is an approximation which clearly becomes better when the frequency is small. Okay, because if the frequency is small compared to the gap, the area of production of excitation would be concentrated around the lowest gap points. Right? That's standard. So the avoided level crossings, so we divide it into different regimes, 1, 2, 3, and maybe many more, which are separated by these avoided level crossing points. Okay, and these are reached. So we can calculate when these avoided level crossing points are reached. They are reached when the energy gap becomes a minimum, because that's the minimum energy gap that you have. And so for low frequency, this impulse region is concentrated around the avoided level crossing point, and therefore the adiabatic impulse become more accurate. Okay. Now to the calculation, so the wave function is now written in the adiabatic basis, where the psi k plus and psi k minus are the instantaneous energy eigenvectors. And I just express the wave function in terms of these eigenvectors, which forms a complete basis with coefficients C1 and C2. Okay. And then we define an evolution operator in the adiabatic basis, which relates this C1 and C2 with their initial value. And the true evolution operator of the system, of course, is given by the relation between the initial wave function and the wave function at time t. And since we can relate these two, because we have already expressed psi of t in terms of C1 and C2, it turns out that this evolution operator is related to the evolution operator in the adiabatic basis by some straightforward wave function overlaps which are given by this. So this requires a bit of algebra, but just accept this. So now for the calculations, the strategy is to track time evolution separately for each region, and in each of these adiabatic region, since we have sort of adopted the approximation that there is no excitation, the system simply gathers a kinetic phase. You drive the system, it just gathers a phase, which depends on the instantaneous energies, and that's the phase that the system gathers. And I'm going to define this xi ik, which is the phase gathered between two avoided level crossing in the nth region. Okay, so in the ith region, that's psi of ik. Now between these two, when these two adiabatic regime, you have an impulse regime where excitations are produced. So within this approximation, we define a transfer matrix which takes the system wave function from one region to the other through this avoided level crossing. And that transfer matrix has off-diagonal element which depends on the probability of excitation production, because if an excitation is formed, the system goes from the ground to the excited state. So the off-diagonal elements gives you depends on the probability of this excitation production, and the diagonal element depends on the probability that the excitation is not produced, which is 1 minus square root of pjk. This pjk is typically called the Landau-Zenner probability of excitation production. These are somewhat well known in the literature, and without getting into the details of the mathematics, let me just say that I can, given the Hamiltonian of this graphene, I can have analytic expression for all this P, R, etc., everything. So now, if there are n such avoided level crossings, okay, and n plus 1 adiabatic regimes, which these level crossings separate, I can write this uk in the adiabatic basis, and by using this wave function overlap, I can get uk, the total true evolution operator. Knowing this, I can diagonalize them, and the eigenvalues gives me the phase band. Okay. So this allows me to obtain an analytic expression for the phase bands in the low frequency regime where standard 1 over omega expansions do not work. Okay, but this adiabatic impulse would work very well. Okay, so let me get into the and here is a plot which shows the match between exact numerics and the adiabatic impulse. So the black line is the exact numerics at every point, and the red dots are the adiabatic impulse. So you see that in regimes where I have, let's say, t, okay, I should have the value of t, capital T somewhere here. So for example, where capital T is of the order 100 or so, which means 2 pi over omega equal to 100, which essentially means omega as 1 over 6 or something like that, 1 over 16 or something like that, really small. You see that this matches almost identical. So this approximation essentially is a complementary approximation to the standard 1 over omega thing, and allows us to sort of tackle the low frequency stuff. Okay, so now let me come to the phase diagram. How much time do I have? 10 minutes? Okay. So, okay, before that, let me just try to mention one thing. So, in this expression, I have the phase band as a function of this wave function overlap coefficient eta, which tells you that what's the overlap between the instantaneous wave function at the final time tf with the original wave function, and this C1 and C2. So let me now ask, when does the extrema of this occurs? Okay. Now that happens when, if I differentiate this with respect to eta, you find that the extremal value of cos phi n occurs when this quantity is, well, the extremal value of cos phi n is given by real parts of C1 and C2 square. Now for phase band crossing, what I need is cos phi to be 1 or minus 1, which means that the sum of squares of the real parts of these wave vectors has to be 1. But we know that because this is a quantum mechanical system and we are ended Konzev's norm, the absolute values has to be 1, which means that C1 and C2, either of them has to be real, right? So this typically happens when either C1, this typically happens when either C1 is 0 and the other one is 1, or vice versa, which, since eta is given by C1 by this quantity, it means that eta has to be 0 or 1. So this essentially means that this phase band crossing is tied to the fact that the wave function overlap between the time at which these phase bands cross and the wave function at t equal to 0 is either 1 or 0. Now 0 is difficult, but 1 is possible because if the Hamiltonian is time periodic, at t equal to capital T or t by 3 in case of the gamma point, there the wave function overlap is 1. Because it's the same instantaneous Hamiltonian with t equal to 0, and therefore the symmetry, you typically expect phase band crossings to occur at those symmetry points, okay, at those values of small t. So let me now get into the phase diagram. So first, for the gamma point, here since this is t by 3 periodic, phase band crossings can happen at t by 3, 2t by 3, or capital T, and the point, and also since the instantaneous energy eigenvalues has a t by 6 periodicity, the the gap here and the gap there, they are two identical value. That's dictated by symmetry, that E of t plus capital T by 6 is equal to E of t. So essentially the probability of excitation formation at these two points are essentially the same, and I denote them by P gamma. And so are the phases, and there is a distinct relation between the kinematic phase that the system gathers at this different region 1, 2, and 3. Okay, and I call this phase by gamma, xi gamma. So, and if you now plug this input into this adiabatic impulse approximation and turn the crank, it turns out that the phase band has a very simple expression in terms of the probability and this angle, which is given by this Tuckelberg phase and the kinematic phase that the system gathers. So now we can analyze the expression for phase band crossing. So if your cos phi is 1, then clearly for any p, the condition for phase band crossing is lambda gamma equal to m pi. That's when cos phi becomes equal to 1. Okay, so you can clearly see if cos phi is 1, then cos 2 lambda gamma has to be 1 also from here for any value of p, and that means lambda gamma is equal to m pi. And this also predicts, and this is a prediction of the adiabatic impulse approximation, that no band crossings can occur at cos gamma equal to -1, which is technically called as a crossing through a zone, Fluke zone edge, whereas this cos gamma equal to 1 is called a Fluke zone center crossing for in this at t by 3. And when we do this numerically, we find that all the crossings that are there occurs at cos phi equal to 1, that is they occur through the Fluke zone center and not through the zone edge. So this matches very well with the exact numerics, and here is the exact numerical phase diagram at t by 3 at small t equal to t by 3, and these are the phase band crossing lines. Okay. And notice that the first such line apparently for at least for this value of amplitude of radiation occurs around t which is much greater than 1. It's roughly around omega equal to 1, and therefore in the high frequency regime there is no phase band crossing for this range of amplitude, but in the low frequency there is crossing at t by 3, capital T by 3. Next we come to this capital 2t by 3, and here we simply need to analyze this condition of phase band crossing by noting the fact that symmetry dictates that the phase gathered from 0 to t by 3 is the same as the phase gathered from t by 2 to 2t by 3 because of this periodicity. And therefore, what are the phase band crossing conditions? So if there is a phase band crossing at t by 3, which means that cos phi t by phi gamma at t by 3 is 2 pi or 4 pi or 0, this also means that this also means that there would be a phase band crossing at 2t by 3 at the same value. So that's one condition. 5 minutes? Yeah. And however, you could also have a crossing through a zone edge, because what happens is that if cos phi takes the value 0 or phi takes the value pi by 2 at capital T by 3, then it will take the value pi at 2t by 3 because the same phase is also going to be gathered, which means that cos phi gamma at 2t by 3 could be -1 provided cos phi gamma at t by 3 is pi by 2 or 0. Okay, cos phi, yeah. So that allows us for a crossing through the band edge, and this happens when cos 2 gamma by plus p by 1 minus p is 0, and this tells you that this equation will only have a definite solution for p gamma less than half. Because if p gamma is greater than half, you need cos phi greater than 1 to less than -1 to satisfy this, which doesn't happen. And we see that if I now plot this numerically in the alpha t plane, what happens is that the edge of this, so these red crossings are the ones where the crossing is through the zone edge, and these red points exactly terminate at the line p gamma equal to half, stating that beyond p gamma equal to half, you really do not have any crossing, which also agrees with the adiabatic impulse approximation. We can do similar things at gamma, okay, at t equal to capital T, and the adiabatic impulse approximation sort of tells you that there are bounds on the value of p gamma, and those bounds are very well satisfied in this numerical plot, okay, that we see. And now let me quickly come to the k point, which is another thing. And again here by symmetry we can fix the value of p's to be the same at each of these crossings. And we find that the cos phi has a generic expression like this. And for cos phi equal to plus or minus 1, that's the condition that one needs to satisfy, which again tells you that there would be no phase band crossing either through the zone edge or through zone center if you have pk greater than 3/4. And this blue line is the pk greater than 3/4 line. This is numerical data. And you see that there is a distinct region where pk is greater than 3/4, where there is no crossing whatsoever. Okay, so the adiabatic impulse approximation tends to predict these aspects of the phase diagram quite well. And then we sort of took this gamma, k, m and x points, all the crossings from there, and put this out. So just superpose them essentially and to get this phase diagram. So each of this closed region in this phase diagram represents a region with distinct Chern number. Although at these frequencies we have great numerical difficulties in computing these Chern numbers. We have done a few, but it's really impossible to sort of do this for all points on the phase diagram. However, each of these things correspond to a Chern number change of 1 or -1, and larger change in Chern numbers means that there are several points which coalesce together. But I must say that the computations of this Chern number numerically at low frequencies are a big challenge. Okay, and there are fluctuations of this Chern number, which, as shown by some papers recently, and it's not so easy to sort of stabilize them. So here is our calculation of the Chern number change at the phase band crossing point for some values of omega and alpha. This is for alpha equal to 2.4, and I think capital T was roughly around 6, which is omega close to 1, and but at much lower values of, or much larger values of capital T, this becomes really difficult because the gap closes, and there is the stability of the Chern number calculation becomes a problem. So let me stop here and just say that sorry I had to skip many details because of shortness of time, but let me just point out that this adiabatic impulse approximation may provide us with a method for looking into phase diagram of this for topology change of these driven systems at low frequency, and so these methods could also be applicable to other systems such as Dirac cones on the surface of the topological insulators, also for while, because it's just a 3-dimensional extension of this 2x2 structure. And I think we are going to look into this in future, and thank you for your attention.